Hello, welcome to this new video from Education channel. This is for class 12 physics. We are continuing chapter 1, charges and fields. The topics discussed are continuous charge distribution. What is charge distribution? Types of charge distribution. What is charge density? Unit of charge density. Types of charge density. Electric field and force due to continuous charge distribution. Watch the video completely without skipping, and if you think the video is useful, do subscribe the channel now and also press the bell button near it so that you get intimated as soon as videos are posted. Our topic is continuous charge distribution. But before that, we will discuss a few points regarding conducting systems. A conducting system is one which conducts current. Conducting systems are broadly classified into two. One, discontinuous system, and the other, continuous system. This is an irregular object. When certain objects are charged, the charge accumulates unevenly, that is, in different numbers in different regions of the object. Such a distribution of charge is called discontinuous charge distribution, and the system is called discontinuous system. There is considerable space between the charges, and we say the distribution of the charge is discontinuous, that is, discontinuous charge distribution. In such cases, the charge is assumed to be concentrated in the center of the object, and we call them point charges. In the previous videos, we were discussing point charges. For point charges, the field and force experienced by a point charge was discussed and calculated using Coulomb's law. If you have not watched those videos, click the I button where I have given the link for Coulomb's law. The other videos you can watch from the playlist. I will give it in the end card. In continuous systems, there is no space between the charges. The charges are said to be continuously distributed. Depending upon the manner in which the charge gets uniformly distributed or evenly distributed, it is classified into three types. 1. Linear charge distribution. 2. Surface charge distribution, and 3. Volume charge distribution. We will take up the first case, that is linear charge distribution. We will take the example of the infinitely long wire and the ring from among the diagrams that are given here. In the case of the long wire and the ring, when they are charged, the charge gets distributed evenly over the entire length of the material. Ring is nothing but a long wire kept in the form of a ring. Such a distribution is called linear charge distribution. In order to explain linear charge distribution, we make use of a quantity called linear charge density, represented by the letter lambda. What is linear charge density? It is equal to total charge divided by length. If we consider the length of this whole wire as equal to L, then Q is the total number of charge present in the whole length L. We may define linear charge density as the total number of charge present in 1 meter of length. Unit of linear charge density is coulomb per meter. We will consider a long wire and electric field due to all the charges present in the wire at the point P at a distance r. Coulomb's law cannot be applied as such in this case to calculate electric field. This is because all the charges in the wire are not concentrated at the same point. It is distributed continuously throughout the wire. To solve this problem or issue, it is assumed that the wire is made up of large number of small portions called dl. electric field due to each such dl is calculated, and then they are integrated to get the net electric field. Number of charges in each dl can be considered as dq. As dl is very small, this dq can be considered as a point charge, and Coulomb's law can be applied to calculate the electric field due to dl. Number of charges in 1 meter of the wire is equal to lambda, the linear charge density. So, number of charge in dl will be equal to lambda into dl. So, lambda into dl is equal to dq. dE, the electric field due to dl, is equal to 1 by 4 pi epsilon naught lambda dl by r square. R is the distance of the point from dl. Lambda dl is equal to dq. To get net electric field, dE for each and every bit of dl is calculated and the whole thing is integrated. 1 by 4 pi epsilon naught will be common in all the expressions, so it can be taken out and the rest only need be integrated. So, integrating dE equal to net electric field E will be equal to 1 by 4 pi epsilon naught integrating for the whole length L lambda dl by r square. So, this is the expression for electric field due to linear charge distribution, a type of continuous charge distribution. Supposing a charge test Q is placed at P, then the force experienced by Q at that location will be an integration of the force exerted by each and every bit of dl on Q. I will write the final equation for the net force experienced by Q. Integration of dF equal to net force is equal to Q by 4 pi epsilon naught. What is the expression for force? 1 by 4 pi epsilon naught Q1 Q2 by r square. These are the two charges. Let this be considered as Q1 and the other one as Q2. We will take test Q outside. So, it becomes Q by 4 pi epsilon naught integrating lambda dl by r square. Lambda dl is Q1 and Q is Q2. Okay. In the vector form, r square becomes magnitude of r square into direction of r, that is r cap. Let us sum up what we have discussed so far. We discussed the type of conducting systems, type of continuous charge distribution. Under that heading, linear charge distribution, definition for linear charge density, unit of linear charge density, how to calculate electric field and force due to linear charge distribution. Let us pass on to the other two types. Let us continue. We have seen line charge density lambda is equal to Q by L. Its unit is coulomb per meter. We will take up the second type, surface charge distribution. We will take the example of this long sheet and sphere to explain surface charge distribution. When this type of materials are charged, the charge resides on the surface evenly. As the charge gets uniformly distributed on the surface, it is called surface charge distribution. In order to explain surface charge distribution, the quantity that is used is surface charge density, represented by the letter sigma, equal to Q by A, the area. The unit is coulomb per square meter. To find the electric field due to this plane sheet at a point P which is at a distance of r, this sheet is assumed to be made up of small areas called dA, and then the electric field due to each dA is considered and then it is integrated. Here dq will be equal to sigma dA, then integrating dE equal to E for the whole area will be equal to 1 by 4 pi epsilon naught integrate for A sigma dA by r square. If a test charge Q is placed at this point and if the point is at a distance of r, what will be the force experienced by Q? What do? We follow the same principle which we followed in the case of linear charge distribution. Calculate the force exerted by each dA on the test charge Q and then integrate. Integrating dF equal to F will be equal to Q by 4 pi epsilon naught integrate sigma A by r square. Q is a magnitude of the test charge for the whole area. In the vector form, it becomes magnitude of r square into direction of r cap. So this is the expression for electric field due to surface charge distribution and force due to surface charge distribution. Now the third type, volume charge distribution. Volume charge density is used to explain this term. The symbol is rho. Rho is equal to Q by volume. Let us consider this diagram that I have given there. It is a non-conducting material. When an object of such material is charged, all the charge gets accumulated in the volume of that object, that is, inside the object. Charges cannot come to the surface. Such a distribution is called volume charge distribution. We have already said that this quantity is explained using volume charge density rho. If the total number of charge present in 1 unit volume of this material is equal to rho, then the charge present in dV is equal to rho into dV. Unit of rho is coulomb per meter cube. To calculate the electric field, just as we did in the previous cases, this entire volume is split into a large number of dV, that is small volumes. The electric field due to each such dV is calculated and the whole thing is integrated. Integrating for whole volume, dE is equal to E equal to 1 by 4 pi epsilon naught integrating for whole volume sigma dV by r square. Similarly, what will be the force? Integrating dF for the whole volume will be equal to net force equal to Q by 4 pi epsilon naught integrating for whole V sigma dV by r square. In the vector form, this will be magnitude only r square multiplied by r cap. I hope this video was of great use to you. If you think it is useful, do like the video and share it with your friends. If you have not yet subscribed my channel, consider subscribing my channel and also press the bell button so that you get intimated as soon as videos are posted. We will meet in the next video with another useful and important topic. Till then, bye. Thank you very much.